Example 1. First, let's start by determining which species is oxidized and which is reduced. Anytime I see a free element, I'm going to look to see if that's going to have a change in oxidation number. So I know that the Cl2 has an oxidation number of 0. If I look on the reactant side, I see that the Cl in HCl is going to have an oxidation number of -1. So I see that the Cl is going from a -1 to a 0. That means it's being oxidized. And because it's going from a -1 to a 0, it's losing 1 electron. If I look at all the other elements, then I see that the chromium is the other species that's changing oxidation number. In CrCl3, the chromium has an oxidation number of +3. In K2Cr2O7, if I look at the dichromate ion overall, so dichromate is Cr2O7 -2. Oxygen has an oxidation number of -2, and there are 7 of them. -2 times 7 is -14. Now, I have to take into account that -2, so I need the chromiums to add up to a +12, because +12 versus -14 is going to give me that polyatomic ion charge of -2. And that +12 is distributed over 2 chromiums, so that each chromium is going to have an oxidation number of +6. So my chromium is going from a +6 for each Cr and going to a +3. So that's being reduced, and each chromium is losing 3 electrons. Now I'm going to write the 2 half reactions. First, I'm going to write the half reaction for oxidation. And we said that the Cl- is the species that's being oxidized. So my Cl- is going to Cl2. I'm going to ignore the Cl3 because that's still going to be a -1. So the only change in oxidation number happens between the Cl- from the HCl and then the Cl2 that's an element. First, I'm going to balance the chlorine, so I need to put a coefficient of 2 in front of that chloride anion, and then I have to even out the charges. So on the reactant side, I have a -2, so then on the product side, I need to put 2 electrons to have the same charge on both sides. Now I'm going to write the half reaction for reduction. So I'm going to keep the polyatomic ion together. So Cr2O7 -2, because that's covalently bonded together. And then if I look at the chromium chloride, that's ionic, so I'm going to just look at the chromium +3. If you imagine the net ionic equation, that +3 is going to be dissociated. Then I'm going to balance the chromium, so I need to put a coefficient of 2 on the product side. The next step is to balance the oxygens, so I need to add H2Os to balance out the oxygen. So on the product side, I'm going to add 7 water molecules, because remember, all these reactions take place in aqueous solution, and that 7 water is going to balance out the oxygen. Then I have to balance the hydrogen, so I have 14, because 7 times 2 is 14, so I need to add 14 hydrogens to the reactant side. So I balanced my chromiums, I balanced my oxygen, I balanced my hydrogen. Now I have to balance out the charges by adding electrons. So on the reactant side, I have 14 positives, -2 from the polyatomic ion, so that's going to give me an overall charge of +12. On the product side, I have 2 times a +3, which gives me a +6. So I need to add 6 electrons to the reactant side in order to even that out. So I'm just going to squeeze those in here on that reactant side, because that way those +12 minus 6 negatives is going to equal a +6, and I'll have a +6 on both sides of the reaction. Now I'm going to combine the 2 half reactions, and I need to make all the electrons cancel out. So because I have 2 electrons in the oxidation reaction and 6 electrons in the reduction reaction, I'm going to multiply the entire top reaction, the oxidation reaction, times 3. And that way, when I combine the 2 equations, all those electrons are going to cancel out, because the electrons that are lost by the chloride are going to be gained by the chromium. So then, when I put all those together, I cancel out the electrons, and I look to see if I can cancel out any waters or H pluses. I don't see any to cancel out, so let's go ahead and put these together. So I end up with 2 times 3 is 6 chlorides, and I have 14 H pluses, and I have a dichromate, And all of that's going to yield, and I'm going to write this underneath so I don't run out of room. I'm going to have 3 times 2 is chlorine plus 2 chromium plus 3 ions plus 7 H2O. Now, in some contexts, you could end here and call it a day and just make sure that everything is balanced on both sides, but we want to recombine this back into a molecular equation instead of a net ionic equation. So if we look back at our equation at the very top of the screen, we see that the H plus and the Cl minus must have come from the molecular acid HCl. So let's think about this mathematically. So the H plus, the 14H plus, must have come from 14 HCl quote-unquote molecules or formula units. Obviously, the dichromate ion would have come from K2Cr2O7. In this case, the K is a spectator ion. And then we have only 6 chlorides. Those 6 chlorides would have come from the 14HCl. But then that leaves me with, if you think about the 14HCl, that leaves me with 8 more chlorides that are so far unaccounted for. So let's see if we can figure out where those come into play in this equation. So 6 of the chlorides are spectator ions in that Cl minus 1. And if you think about where are those going to be on the other side, well, those 6 chlorides would have been bound up with the chromium plus 3. If I think about my net ionic equation, if I have 2 Cr plus 3s, there are going to be 6 chlorides that go with it. So the 6 chloride spectator ions on the reactant side, I know that those ended up as 6 chloride spectator ions on the product side. Now 14 minus 6 is 8, so I have these remaining 8 chlorides. And 6 of those 8 were oxidized. So if I look at my 3Cl2 on the product side, okay, so 3 times 2 is 6. So then of those remaining 8, 6 of them got oxidized into the diatomic chlorine. 8 minus 6 leaves me with 2 more chlorides that I have to account for. But we have to think about the potassium. If I look at the very top of the equation at the very top of the screen here, remember that the potassium is in potassium chromate, and so it's K2Cr2O7. So I do have those K plus 1 spectator ions. And if you look at the equation at the top then, on the product side, those K2s go into a KCl. And we know that anything with group 1 ions are gonna be soluble, so those are gonna be spectator ions in that case as well. So the 2 K pluses on the reactant side are still gonna be 2 K pluses on the product side. So those remaining 2 chlorides are gonna quote unquote combine with the 2 remaining chlorides on that product side. So now let's recap and put all of that together into a balanced molecular equation. So we said that 14H plus came from 14HCl, and then we said that the dichromate anion came from K2Cr2O7, potassium dichromate. And then on the product side, I have 2 KCl and 2 CrCl3 and my 7 waters and my 3 chlorines. Now I want to go back and make sure that my reaction is balanced on both sides. So first, let's start with my hydrogen. So on the reactant side, I have 14. On the product side, I have 7 times 2, which is also 14, so that's balanced. Then I want to check my chlorines. On the reactant side, I have 14. On the product side, I have 2 from the KCl, I have 6 from the chromium 3 chloride, and I have 6 more, so that gives me 2 plus 6 plus another 6, which also gives me 14. So my chlorines are balanced, and that was the tricky one. And then I check my potassium. I have 2 on the reactant side, and then I know I have to then have 2 on the product side. So that's why I balanced this with a 2 there. Then I look at my chromiums. I have a typo or script O there. That should be a dichromate anion. So that gives me 2 chromium on the reactant side, 2 on the product side. So that's balanced. And finally, I'm going to check my oxygen. So I have 7 on the reactant side and 7 on the product side. So that is balanced. So my full and complete balanced redox equation, my molecular redox equation, is right there circled. Ta-da!